Hello, Per-Ola Malmqvist, fire protection engineer and former battalion chief from Sweden here. I've made a video for the Swedish fire brigades about explosions due to lithium-ion batteries. And I thought I'll record it in English as well to be able to share it with you. I'm looking at the consequences at some incidents there have been with explosions due to lithium-ion batteries. And the reasons why it can explode. And what I found that will be useful, and what I'm talking about in this entire video is things that we have learned from 120 years with fossil fuels, where we've had tons of explosions and fires due to that. And a lot of that knowledge we can just put into its lithium-ion battery context here and reuse. And here is what I'm thinking about. If we consider lithium-ion batteries like a gas cylinder with flammable gas, then we will have about the same properties from a firefighting and a fire perspective. They can leak, and that's what we see in the lower part of the image here, a leaking gas cylinder and battery giving away smoke. And in the upper part, we have the flames coming from the gas cylinder and from the lithium-ion battery. And if we apply this knowledge that we have on lithium-ion batteries, then we've come a great step forward, I think. But I will start talking about a couple of incidents that have happened in the world. And this one was in Germany this summer. It was an EV that had a smoking thermal runaway, and it exploded from the gases, and the roof went off the building. The walls, the brick walls, they fell. The garage doors was pushed out. And if you look at the building in the background, you can see that there were roof tiles that were like shot away from that roof. But the interesting part was that if you look at the other side of the building, I don't have the image here, but then you could see, I will leave a link in the description to some better images of this, where you can see more details. And there you can see that the explosion went through the house and smashed windows, or pressured the windows broken on the other side of the building. So a huge force from this one. Here you can see the brick walls that is laying down in the background. And you also see that there is not much fire damage it's just on the vehicle itself, and then you don't see much fire besides that. And here, if you look at the background, you can see that the vehicle next door, there is no license tag on it, and there are no windows in it. And I'm thinking that if that happened due to the explosion, there have been a lot of force in it. Here is one of the garage doors, and you see parts of the roof laying on the street as well. And this here is about what it probably will have looked like before the explosion in the garage. Smoking thermal runaway from the vehicle, and then you will get an ignition, and then you have the gases ignite, and now we start a fire here. But it's a very characteristic of a lithium-ion smoking thermal runaway, the white grayish smoke, and you see what force there is in that explosion that we get from that. Here is another one from Belgium at the fire station, and it was closed for the firefighters, so they got there during the period when it was a smoking thermal runaway. And if you look here, the roof will leave the vehicle pretty soon in the explosion and land. And fortunately, all the firefighters were okay. And about this specific incident, there is a very good video that digs into details about that I will link to in the description here. Next one is this one. And this one is from 2019 in China. And I didn't really believe at that point that an EV could have that kind of explosion, that kind of power. But when looking at it now, if we stop it right here, you can see the white grayish smoke that is so typical for lithium-ion batteries. This is before the explosion occurred, and something have happened that made the firefighters use protection when they behind the cars when they were going to attack this vehicle. And as you see here, it's the typical lithium-ion smoke and a lot of power in that explosion. This one is the next one. Again, very interesting. Now we have a lithium-ion battery in a battery energy storage system. And you see the cracks in the building, in the wall. This was in Germany last month or 2 months ago. And the wall, you can see that the wall was broken. Here you see that parts of the building's walls are missing. And it was a battery energy storage systems, lithium iron phosphate batteries, 3 units of 10 kilowatt hours each about. And I suppose that it's only one of them that went into thermal runaway at first. So this could be due to a only 10 kilowatt hour lithium ion battery that we get this kind of damage. And you see it's thick brick walls and a lot of damage to the construction. Here is another one that is very, very interesting to see. If you look at we'll go here again. Again, fortunately, no one was hurt. And there was a firefighting operation going on. You see the hose going in through the door. And here you see the pressure starting to open the door. And you see the grayish smoke that is from that. And then when we have had a combustion or in the combustion, it's almost no smoke left. And that is also something that seems to be typical for lithium-ion battery fires, that when you have the combustion, you get no smoke. So, and what I understand is that it's from the aerosols, the white things in the smoke, the aerosols, they are electrolyte that will combust together with the gases when they combust. And I show you a lot of videos here, and thanks a lot for the fire brigades and the companies that is sharing these videos, because there are so much to learn and look at in this setting. I'm glad for this guy that he is okay with some scratches on his helmet, as I learned. There were 3 incidents in Germany with explosions, 6.5 kilowatt hours lithium-ion batteries energy storage systems. 2 in multifamily houses and 1 in a one-family house. And in all cases, the explosions from this small energy storage system, 6.5 kilowatt hour, broke windows, opened doors, and in one case it lifted the roof and it landed again, but it was huge force from this small BESS battery. And we have had those in Sweden as well. Here is one incident from Linköping in Sweden. And if you look at the left circle, you can see that there used to be a window in that hole. There is a window missing, and that window is laying on the grass at the right circle. And you can see that it's the frame that have been pushed out of the window hole. And you can also see the cracks in the building at the side there. If we go inside and take a look at what caused it, it was an e-bike battery. And the owners of the building or the apartment, they saw that there was something going on. There was a leak of electrolyte from the battery. it was charging. I think they pulled the plug, and then they went to get something to swipe up the electrolyte with. And when they were out from this room, they heard the door slam and the explosion, and that's when the window was pushed out. And the door was probably slammed close due to the pressure and the speed of the gases that wanted to get away from the room. And when the door was shut, then it had to take the other way that was the easiest with least resistance, which was through the window. And here is a similar instance. It was a scooter in Sydney at a hostel. And you see here that they had from standing there and just observing that something was wrong, you get this very fast, rapid fire. And if we take a look at what happens here, it looks really cool here. Not much to see, I think. Something is going on. And then from that we have this here. And here you see that we have flames in the entire opening. And that is a sign that it's not the object that is burning, it's the gases that are burning. So the battery released enough gases to give us this kind of a flame in the entire door opening. And if this was similar to the one I spoke about in Linköping, if the door would have been shut here, we would have get some damage on the construction instead. Here is another very, very good video because it shows us the properties to look out for if we are in a larger setting indoors with a battery fire. Normally the white smoke is something we don't think is bad. White smoke is good. But when we talk about battery fires, that is not the case. I'm going to see. That was not my intention here. I'm going to try to go back to this one. Here we go. If we look at the floor, you can see that we have white smoke going like it's heavier than the rest of the air, and it's moving across the floor in batches here. It might be when they're opening doors, etc. But this light smoke wouldn't be something to be very concerned about in a regular fire. But with the knowledge we have now, and if we have batteries involved, this could be an indication of something bigger going on. And I'll stop here at around 8 minutes. Here we go. If you look at the upper right corner now, you will soon see the same kind of ignition as we saw, but in a larger scale. I'm always wondering if this video really is working or not. Now it should be working here. Yes, some movement. Anytime there will be an explosion in the upper right corner. And you see it's huge forces that wants to go somewhere, or the gases wants to go somewhere. So it's something to be aware of, the white gases. And the reason for this, I have made a video earlier about battery fires. But if we only look at the explosions, we have the electrical energy and we have the electrolyte in form of a flammable liquid and lots more. And the electrolyte, the molecules for the electrolytes look like this. It's hydrogen, the white small bulbs, it's carbon, the black and gray ones, and it's oxygen, the red ones. And when we add energy, this was something I couldn't get my head around in the beginning when I started to learn about lithium-ion batteries. Because we have been taught that energy can't disappear. It has to go somewhere. But where did the energy go? I first thought that the energy went to vaporize the electrolyte, which maybe parts of it does, but it also breaks down the electricity in the energy that is charged in the batteries will break up the bonds between the molecules and the atoms in the molecules. So we will get other gas substances or gases like carbon monoxide, carbon dioxide, hydrogen, and various hydrocarbons. And this explains this video that I made also from an earlier video I have. When we have 90% state of charge, the energy in that battery will break down the molecules very much, and we will have a lot of flammable gases that is released, and so much energy that it ignites in this case. At the 60% state of charge, we got the smoke, and we also have the breakup of the gases, the molecules into smaller molecules. And at the 20% state of charge, nothing happened for 29 minutes. And in all cases, I had 350 degrees C at the battery. And this one is also a video I've showed before with the propagation of the fire, that it goes from cell to cell. And it's the same thing when we have a smoking thermal runaway. It will move from one cell to the next cell, and it's the time between the propagation, between the cell to cell, that will determine how much gas we will get and how fast we will get that gas in the room or in the volume where we are at. And this is a report from 2022 about how much gases are released at different state of charge. They had 50, 100, and 150 states of charge. And if we look at the 100% state of charge, it was 0.33 liters per watt hour of battery. And what was produced, if we take the 100% state of charge, it was around 30% carbon dioxide. And carbon dioxide is not flammable. But the rest of the things that was produced, carbon monoxide, hydrogen, and hydrocarbons, they are all very flammable. And hydrogen is like 27.7% of the gases produced was hydrogen. And hydrogen's flammability limits are between 4 and 74% in air. Carbon monoxide is 12 to 75% in air. Methane 4.4 to 16. And as a reference, we have propane that is 1.5 to 11.7. And all this is knowledge that we have since before, that we have learned from industrial use of hydrogen, from natural gas explosions and experiments with that. We know about the lower explosive limit, the upper explosive limit, and the ideal mixture. And for the battery fire kind, what we, instead of having an opening that we open that release a certain amount of gas each second, we will have the cell releasing gases when they start to get in thermal runaway. And we will build up the level that so we get into the lower explosive limit. This is another good report from the University of Texas and Sandia National Laboratories, where they ignited different mixtures of battery gases in a sealed container and measured the pressure. And they landed in between 3 and 7, 8 bars of overpressure. And bar is a good unit to measure it in, because it's simple to understand how much it wants to expand. If we have a 3-bar overpressure, it wants to expand 3 times. If we have a 7-bar overpressure, it wants to expand 7 times. And if we look at that compared to when things rupture in buildings, windows, interior doors, light walls, double gypsum 2x13 millimeter plasterboards, it's 0.02 to 0.05 bars, or a brick wall that is 0.2 to 0.35 bars. So we're a factor 10 when we're at the minimum here if we have an entire room filled with the flammable gases. A factor 10 to bring down brick walls. And so sometimes people ask, what about ignition? What could ignite this kind of battery explosion? Well, the big difference between a lithium-ion battery and a gas canister is that the lithium-ion battery have the ignition source readily available inside in form of the energy that will heat the parts of the battery that it touches on its way out and heat them up. And if a surface is getting over around 400 degrees C, we will have an auto ignition of the gases. And at the same time, we will have sparks flying from the short circuits that is going on inside the battery. And the same thing here, the temperature will increase the more time we get into the propagation between cell to cell. If we want to calculate this, because the gases that we can produce, if we take a 500 watt hour battery, which is e-bike, a small e-bike, I think, battery. If we have a room at 2.4 meter, 8 feet high, state of charge on 100% and a lower explosive limit of the gas mixture at 10%. So we get 0.7 cubic meter or 0.7 square meter of floor area where we have a flammable mixture if the entire 500 watt hour battery will disperse evenly in an area. And 0.7 square meter or 7.5 square feet is much smaller than a regular room. So that makes us, or me, wonder, how could we have this kind of explosions from a bike battery like we saw that pushed the window out with that kind of forces? Well, the thing is, if we have a gas volume, that gas volume in the 500 watt hour case is 1.7 cubic meter of gas within flammability limits. And if we look at the pressure from that one, 3 to 7 bars, if we get 7 bars over pressure, the volume want to expand 7 times, and in a very short period of time. So a gas cloud of 1.7 cubic meter in a 20 square meter room with a 7-time expansion gives 0.25 bars of overpressure in that room. And if we go back to the table here about when things rupture in buildings, we have 0.02 to 0.05 on the lighter details and 0.2 to 0.35 bars on a brick wall. So we are well within those for even a small ignition of a vapor cloud in an enclosed space. And this is a way to demonstrate that if we have a big opening and we have the expansion of the gases, then the gases will go out there and it won't affect the construction. But as on the right side we have a smaller opening and we have the expansion and the gases can't take that way. It wants to go somewhere, and that will be through the smallest part, not smallest, to the easiest part, the weakest part of the room where it wants to exit. So with this said, watt hour and room volume is not enough information to make any conclusions because even the smaller batteries, as we have seen, can create enough pressure to do things to the construction. And those bad things to the construction could be that it will remove the fire protection in form of firewalls and fire doors, etc. So maybe a large bass with a slow propagation time is better than a small bass with a fast propagation time. Maybe. It all comes down to ventilation and construction of the energy storage systems and the room and the ventilation. And if we compare this to other fires, normally we want to close the doors around the fire. And in this case, that could be a bad thing because an open door could be a safety precaution. To have a well ventilated fire where we don't let it become a explosive mixture of gases. So different gas proportions, room volumes, and the amount of battery gases will require different vent openings to be safe. And here is also, there is a lot of engineers out there that knows a lot about explosion and how to construct, dimension the necessary explosion openings to don't have an explosion damage the construction, which is information that is learned through several years with problems from natural gas, propane, hydrogen, and other things in an industrial setting. And I've been speaking about deflagration, which is combustion slower than the speed of sound. Maybe there can be detonations when we have hydrogen involved and this kind of gases. And maybe that one explosion in Germany was a detonation. I don't know because I know too little about the detonations. I will leave it with that what I'm saying here is valid for deflagration, which is a nicer case than a detonation. So I'm on the good side, so to say. If we have this kind of battery gases on the outside, here is a 50% state of charge vehicle battery. I'll pause it right here. You see how close he is with the propane torch to ignite the gases. And he was trying in the gas cloud a meter away from it and it didn't ignite. And we had some wind in this situation. And I think that when we have some wind and the smoke is on the outside and it's not accumulating somewhere, then we will have a pretty safe situation from an explosion perspective. It's when the gases are allowed to accumulate that we get the problem. I'm going to show that again. Here we go. And as you see here, we can have some smoke coming from certain parts of the battery, and then we have the flames from other parts of the battery. And the smoke that we see still is not combusted. So if that is allowed to accumulate, we will still have the problem where it's allowed to accumulate. So even if we have a flaming combustion on some parts, we need to be aware of the smoking thermal runaway as well. Here is the same kind of battery, 100% state of charge. And if you look here, it's what I want to show is the ignition source that we were talking about a little bit earlier. We have the smoke coming from where the problem is in the battery, and soon you see the sparks, and we get the flame, and then we get the flaming combustion, and in the beginning a pretty small flaming combustion, and after a while it increases in speed and becomes hotter and hotter here. So that is an important thing, and that's just the same as with any gas leak operation. If you can see flames, you have a pretty good situation. If you don't see the flames and you have a gas leak, you have to work it a different way. So if smoke is allowed to accumulate from battery fires, think gas leak. Also make a kind of assessment considering the size of the battery and the room volume. A cell phone battery in a room is not an explosion hazard. But when you get larger batteries, and then you need to consider exactly what is where the limit is. I don't know that yet. And treat confined spaces filled with smoke like they can explode. And that is, think gas leak again. Define hazard areas and no-go zones like if it was a gas leak. Inertia about the confined spaces before ventilation is something I don't know much about. And if anyone out there have more information about this, in which situation it will work and when it won't work, please feel free to email me, because that would be great to learn more about that. Open openings from a safe place. Yeah, being the right side of the door so the door can't hit you if there is an explosion when opening the door, for example. Don't stand just behind the windows that can be blown out if there is an explosion. And ventilate early and continuously could be a way to do certain operations to keep the rooms below lower explosive limit. If it is possible, there will be tons of situations when it's not possible. But if it's possible to ventilate, that might be a good thing. If you have fire and no smoke, that is a good situation, just like for a leaking gas bottle. So don't close all doors if it's not necessary. Let it get the oxygen it needs to burn, if that is possible. And if the fire, as we saw on the battery earlier, there's both smoke and fire, look at the smoke where it can go so it's not allowed to accumulate somewhere. And that could be something to work with PPV fans, for example, to clean the spaces from smoke where it's accumulating. If that is a car outside, that could be something to, like a PPV fan, pushing the smoke out of the car could be one way of making the scene safer. And this is the final picture again, the same video I started with. If we think gas leak when we have lithium-ion batteries, then we've come a long way in our understanding of how to make operations. And if anyone have more knowledge about or thoughts about the operations, please send me some information about it, because I'm eager to learn. And I'm sure that there are a lot of smart people out there doing good stuff. So please share with me what you think. Thank you very much. Bye.